Hello everyone, welcome to Learning by Solving YouTube channel. This is GATE 2021 Electronics and Communication Engineering question paper. This is 1 mark question number 6. Let's try to solve this question. A bar of silicon is doped with boron concentration of 10 to the power of 16 per centimeter cube. So that is nothing but this is p-type semiconductor. It becomes p-type extrinsic semiconductor. So the concentration of doping acceptor concentration, that is Na, is equal to 10 to the power of 16 per centimeter cube is what is given in the question. And assume it to be fully ionized. It is exposed to light such that electron hole pairs are generated throughout the volume of the bar at the rate of 10 to the power of 20 per centimeter cube second. So is saying that this semiconductor is exposed to the light so that electron hole pairs are generated. So that generation rate is given, that is generation rate is equal to 10 to the power of 20 per centimeter cube second. So this is the generation rate. And if the recombination lifetime is 100 microseconds, so recombination lifetime is also given, that is 100 microsecond. So let's denote here it like this. And the intrinsic carrier concentration of the silicon is 10 to the power of 10 per centimeter cube. So that is Ni is 10 to the power of 10 per centimeter cube. So this is what given in the question. So what is asking actually? So is asking it is 100% ionization of boron, then the approximate product of steady state electron and hole concentration due to the light exposure. Is asking the steady state product of the electron and hole concentration due to this light exposure is what is asking. So let's try to find out with the given information this generation rate. So what is the generation rate here? So generation rate is defined as the excess electron or excess hole concentration by carrier lifetime, minority carrier lifetime. So that is delta n by tau or delta p by tau gives the same value. So we can find the electron and holes which are generated due to the light source from this generation formula. So let's try to find out that one. So now delta n is equal to delta p is equal to generation rate into lifetime. So what is the generation rate? 10 to the power of 20 per centimeter cube second into what is the carrier lifetime, that is 100 microseconds. So 10 to the power of minus 6 seconds. So now simplify, then you will get 10 to the power of 16 per centimeter cube, that is delta n is equal to delta p is equal to 10 to the power of 16 per centimeter cube, which is the electron and hole generation due to the light source exposure. So now next what is asking the approximate product of steady state electron and hole concentration. So we need to find the steady state electron and hole concentration. So what is that? So since it is p-type semiconductor, so pp is the representation that hole concentration in the steady state in the p-type semiconductor. So that is nothing but pp naught plus the excess electron and hole generation due to the light source. So what is pp naught here? Pp naught is nothing but Na plus delta p. So what is Na in the question given? Na is 10 to the power of 16 here. So let's substitute here in the 10 to the power of 16 plus what is delta n or delta p, that is 10 to the power of 16. So that is 2 into 10 to the power of 16 per centimeter cube is pp, steady state hole concentration. So let's find out the steady state electron concentration now. So n in p-type semiconductor, so that is np here, that is np naught plus delta n. So now what is np naught? So np naught is ni square by na. What is ni square? So in the question he already mentioned that ni is 10 to the power of 10, 10 to the power of 10, so that becomes 10 to the power of 20 when you square it, and na is given as 10 to the power of 16. So what it is, that is 10 to the power of 4, 10 to the power of 4 for 10 to the power of 4 per centimeter cube, that is np naught. So that is when you substitute that in this equation, so now it is 10 to the power of 4 plus what is delta n here. So delta n here is 10 to the power of 16 per centimeter cube. So let's substitute that here. So that is 10 to the power of 16. So since when you compare 10 to the power of 16 and 10 to the power of 4, 10 to the power of 4 is very less compared to 10 to the power of 16. Since in the question is asking the approximate value, so we can neglect 10 to the power of 4. So now it becomes np is approximately equal to 10 to the power of 16. So now we got np here and we got pp. Is asking the product. So let's do the product, that is pp into np, and that is 2 into 10 to the power of 16 per centimeter cube into 10 to the power of 16 per centimeter cube. This is also per centimeter cube. So what is the answer that you are getting here? That is 2 into 10 to the power of 32 per centimeter power of 6. That is the product of holes and electrons in the steady state due to the light exposure. This is 2 into 10 to the power of 32. This is the correct answer for this question. So let's check the options in the question. So the option D, 2 into 10 to the power of 32 per centimeter power of 6 is the correct answer for this question. Let's quickly summarize what we have done in this question. It gave Na, that is the whole concentration, and it gave the generation rate, recombination lifetime, intrinsic carrier concentration. So these are the things he gave, and he asked to find the product of the electrons and holes in the steady state due to the light exposure. So from the generation rate, we can able to find the electrons and hole generation, what are the electrons and holes generated. So those information we can able to find, we find here. And then the at steady state, what is the value of holes and what is the value of electrons can be find out in this fashion, that is pp is equal to pp naught plus delta p. From there we find the hole concentration, and np is equal to np naught plus delta n. From there we can able to find the electron concentration, and when we product we got 2 into 10 to the power of 32 per centimeter power of 6. So this is the procedure. Thank you so much for watching.